to know. Okay, so lesson 4.3, question 4. Which part of that, or all of it, or should we work through this one? I mean, if you can work through number 4, you probably can do just about anything in the lesson, I suspect. So, the review material is always that suspect, but, give those review questions to keep you exposed to it. Because, eventually we quiz and we test and all that, and you gotta be able to carry some of that along. So the review that I choose, lesson by lesson, are kind of like the high points of previous lessons. It's not just to keep you busy. I know it looks like a lot of work. It seems like a lot of work, but that's Algebra I. It's the nature of the beast. So for 4, the population of Coolville is currently 25,000 and is growing at a rate of 600 people per year. So with that sentence right there, just stop, read all the way down to letter A. It says write an equation for the population of Coolsville. Can you do that? Just from that first sentence.
I didn't understand.
What's that?
I didn't understand.
I think so. I think you can. So let's think about what an equation consists of. When it's written like this is pretty important. This is the basics of the slope-intercept form of the equation. This y-intercept is the starting point in a relationship. That's where things begin. So in the population of Coolsville, what's the starting population in that first sentence? 25,000. So there we go, 25,000. Slope-intercept form equations are rate equations. They're equations that describe rates. So we've got slope-intercept form. We've got standard form. Those are the two different forms of equations that we see. This is like this one here, it's like hot dogs for $2 a hot dog and hamburgers are $2.50 a hamburger and you have $30 to spend. It's that kind of a problem. That's not a rate problem because we're not talking about how fast the hot dogs or hamburgers are being bought or eaten or growing or whatever. But when we have growing and increasing and changing situations, this is the form of the equation that we use. So the slope is the rate of change. Do you guys remember the ambulance problem and the helicopter and the accident on the highway? A long time ago, yes.
Oh, yeah.
2 years ago.
Yeah, I
Remember that? That helicopter would fly at, I forget what kind of speed, but the ambulance would go 55 miles an hour. And the distance it would travel was equal to 55 times the number of hours. That's a rate of travel. And that was your first real introduction to rates, rate of change. And that rate of change at 55 miles per hour was, what we did is we were graphing something like this here. It started at some location and it would go 55 miles in 1 hour. And then it would go another 55 miles in another hour or something like that, or maybe, I forget the exact numbers and all of that, but it was that idea. And then the helicopter was the same thing, but the helicopter would start further back, but it would travel faster, so it had a steeper slope, a higher rate. Well, populations and speed are similar because they change. And they change at a particular rate. They go up or they go down over a period of time. So whenever we're talking about slope, that's a rate of change. It could be speed, it could be population, it could be how tall something is, it could be the temperature. So what you have to look for is you have to look for two things. What is the starting point? That was 25,000. And what is the rate of change in Coolsville population? What is it? How much?
600 a year.
600 per year. So that would be 600 times the number of years, which they told us in letter A needs to be X. And this adds up, and we multiply this 600 by the years, and we add it, and that gives us our population. So those are rate problems. Rate problems always use slope-intercept form. It says write a similar equation for the population of Dull. So there's Coolsville and Dullsville. Across the river is the town Dull, which is currently has a population. So what's the population for that place?
34,900.
34,900, and what's the rate of change?
300.
Per year?
Yeah.
All right, so there it is. So there's Dullsville and there's Coolsville. So this one starts with less people, but it's growing faster. That one starts with more people, growing slower. So they give us graphs of the two. Is that right?
Yeah.
Hold on. It's decreasing by 300 people.
Yeah, I'm gonna say that doesn't look.
Yeah, it doesn't work right.
Wow, they're not good.
So
at
if it's
keeping people
decreasing,
alive.
what's its rate of change?
Losing.
Losing. So negative. There we go. So they start with more, but they're going down.
They're not good at keeping people alive.
That's because it's Dullsville, it's not Coolsville.
Yeah, that's true.
Catchy names. The more you're in this book series, the more catchy stuff they get. So there are your equations. It says to give the approximate coordinates of the intersection or the break-even point. In other words, where the populations are going to be the same. And they give us the table, they give us the graph. So where are their populations about the same?
Well.
How many years?
11 and a half years.
Look real carefully.
About the same?
Well, when are they exactly the same?
11 and a half.
Look at the table.
Yeah. Oh, table. Oh.
Yeah, the line, the graph looks like 11 and a half, doesn't it?
So does the table.
Really?
Yeah.
I see
Oh, I see
31,000.
11, sorry.
I see 31,600 for 11
Yeah.
for both. Yeah, so it looks like after 11 years. So it says until 11 years, blank had a larger population. Who? Dull. They want. I think they say Dull. You do.
So
Yeah.
weird names for places.
Well, yeah, they just do that to try to be funny. So, so after blank had the larger population. So after what, 11 years? Who had the larger population?
Ball.
After 11 years?
Yeah.
Who had the larger population?
Yeah.
No, look at the graph. Which is higher after 11? Coolsville is higher, so they had a larger population.
32,000.
So then at 11 years, Coolsville and Dull had the same population of how many people?
32,000.
Check again. Look in the table.
32,300 is what Coolsville.
Your book the same as mine?
I didn't see this at first.
In 11 years, 31,600,
Oh, yeah.
same population.
I thought you meant 12.
Yeah. So what they're trying to get us to do is say, well, you can get a rough idea by looking at the graph, but you can be much more specific looking at a table. That's the point behind this. So if we write an inequality that represents the values of X for which the population of Coolsville is greater. So for X, let's see, okay, so for Coolsville, when it's greater, X has to be what? More than or less than 11 years? Is Coolsville population greater after 11 or before 11 years?
After.
After, so X has to be bigger than 11. Dollsville has a greater population when X compares to 11. How? So when the number of years is what compared to 11? Greater than 11 or less than 11? You're just guessing. Look at the table, look at the graph. Dollsville has more population when the years are less than 11 or more than 11?
Well.
Less. Yeah. Okay. So that cleans up that whole problem. Do you want to ask anything about anything else? Jackson?
10.
Sure. That's a review problem, isn't it?
Yeah, I'm
Yeah.
gonna
So she's investing number 10, investing 8,450 in stocks. After 1 year, the value of her stocks has fallen. And it's now worth 76.25. By what percent did her stock fall? So it goes from 84.50. And it goes down to I can't remember these numbers. 76.25. So we're looking for the percent of loss. So this would be the portion of the starting amount always. So when we do percent loss, it's going to be the change divided by the starting amount. So it's the amount of change divided by the starting amount. So how much does this, and we have it as a fraction form, and then we're going to change it to a percent by multiplying by 100. So how much change is there? How many dollars? I'm sorry? 820, oops, not a point, $825. And the starting point is going to be 80. Yeah, so if you just hit that on a calculator, multiply it by 100%, you know, what we could do is, you can do one of two things. You could say this is negative, and then you would say it's a negative percent, which would indicate it's decreasing. Or you could write in here, you know, it's a decrease of, and then your final answer would be a decrease of such and such percent. That's more commonly done. So what do we get for a percent there? It looks like it's about,
I got 9.7.
that makes sense, 9.76% decrease. And, you know, if you look at this, 8 out of 84 is about 1/10. So it's a little less than 1/10, that's a little less than 10%, which is 1/10. So we're good, makes sense. Anything else? All right, did you finish that thing while we were sitting here? You did? Yeah, I've got this open and I'll just make such mark, okay. All right, so the next lesson, we're gonna leave this kind of stuff, we're gonna go back to more grind of working with variables and combining like terms and equivalent equations, things like that. Some more mechanical things you might say. So it's 4-4. So here's the title, solving ax plus b is equal to cx plus d. So x is the variable. A, B, C, and D are just different numbers that can be used. So, for example, a problem that's written like this might be something like 4x plus 2. And then over on the other side, it might equal 7x plus 10. That's what we're saying here. We're just saying A, B, C, and D are coefficients and constants. Coefficients are in front of the variable x. Constants are things that get added or subtracted. So this B and D, that could be subtracting or adding. It can go either way. So in general, what we want when we're done with this is just like any other problem. We want to know what x is equal to. So we're kind of going back to things that we've done a few weeks ago, but we're just putting a twist in it. We've got x on both sides. And I don't know what y'all did in spring, but when we were doing COVID spring school, I had a couple lessons on this with you from transition math books. We did some of this kind of stuff. So the whole idea with this is that we use inverse operations. We can add, subtract, multiply, and divide. We can do anything to an equation as long as we treat both sides evenly. So in this case here, always begin with your variables, always. And first thing you want to do is you want to look at your variables, and because I have 4 over here, I have 7 over here, I need to get them together somehow. And you're going to do that by using inverse operations. This is positive, this is positive. So the only way to remove it from one side would be adding a negative or subtracting. And I could do that. I could like subtract 4x from here, but to keep things equal, I have to do 4x over here as well. So if I subtract 4x and I subtract 4x from both sides, everything's still equal. Now, you could have subtracted 7x too, no problem. But the only thing is, when you're done, if you were going to subtract 7x, is you would have negative x's on one side of the equal sign. And it's nice to think ahead and keep everything positive. So in this case here, that 0 cancels. This is left as 3x. You still have the plus 10, and you still have the 2 on the left side of the equal sign. So then now it just looks like a 2-step equation, right? Yeah, you just subtract 10. And then you have 3x is equal to negative 8. So we make a little more room. And then what do? Not subtract, because there's multiplication in here. Divide. So x is equal to negative 8/3. Don't go changing them to decimal numbers. Just leave these like this. What we're doing, what we're trying to focus on with some of this work is just the mechanics of being able to get all of the like terms on the same side of the equal sign using inverse operations, and then eventually narrowing things down to what a single x is. We don't have to worry about dividing and multiplying by negatives because we don't have an inequality symbol. And eventually we'll do more of this work with inequality symbols, and then we have to remember those rules. So let's do this one. And work on it on your own. See how far you can get it. That's right, you guys got white marks. Colors your box, Harvey.
I think it's the red one.
Is it red one? Colors your box, Jackson. Are you
I
green?
got green.
Dawson, what are you?
Orange.
Can I steal a calculator from there?
forgot it was home again.
Yeah, it's probably in the little rolly counter thing on the bottom left. So let's finish this one on paper.
Thank you.
You're welcome. What's your answer? What is Z?
9.5.
9.5?
Yeah.
It's not even a nice value, huh? Do you have it, Marvis?
No, not yet.
Yeah, it's 9.5.
How much? 9.5?
Yeah.
19 over 2.
Yep.
Yeah.
Negative 9.
Negative? I don't have negative.
Yeah.
Yeah, 22, that becomes positive, doesn't it?
That's wrong, it'd be negative 9.5.
Yeah.
Yeah.
Yeah, but look, when you add 23,
I made that an addition of a
Yeah,
negative.
I got it.
but if you, addition of a negative is the same as adding more negatives, and this is already negative.
Yeah.
So this needed to be just the addition of 23. So,
Yeah, I got
take,
9.5 too.
yeah, you take care of the 3Z.
Yeah.
You can't forget to pull that negative down.
Yep.
And now when you add 23, that's 23 minus 4. 19, divided by 2. Z is 19 halves. Okay, do the next one on the board. 9 times the quantity, 9 minus k is equal to 6k minus 1. 9 times the quantity, 9 minus k is equal to 6k minus 1. So what do you have to do before you do anything else? Yeah, distribute. Yeah, just get the fraction form and simplify it.
Just keep it like that.
81 to added 81. But then that's 81 and you added 81, so you have 161. Sometimes you just stick yourself in there with change things to negatives. 9 times 9 is? Oh, I'm sorry, 18.
9 plus 1.
Yeah.
I got 10.
So what did you get for the first line? 81,
81 subtract 9k.
yeah.
Is equal to 6k.
Oh, that's tough, okay. And then what?
81 subtract 3k because you said subtract 6k from 9.
If I subtract 6k from both sides, that turns into a negative 15. I,
Add them.
yeah, add the 9k's. And you have 15k.
Yikes, I messed up that.
And then you get to do what?
Add.
Yeah. Add the 1. Yeah, that's not a pretty number, 82/15. Just leave it as it is. The point is not so much finding any kind of a decimal or what have you, it's just getting the inverse operations straight. Okay, so let's do one more and get you going on this stuff. This one, put this one in your paper, on paper in your notes, okay? 7 subtract. Quantity x plus 5 equal to 4 times quantity x plus 11. So this one here is the always been a sticker with us. It's always been challenging.
Negative.
7, gotta remove the parentheses, and when you have a negative in front of the parentheses, what does that do to everything inside? Makes it negative, or its opposite. So subtract x, subtract 5. Then what? What should I make this into? Yep. So,
Add 5 to both sides, get rid of that.
yep, start by, yeah. Get rid of that.
And multiply 7 by 5.
No, we don't do that, because it's subtracting this. That's not multiplication. So this is like saying subtracting one set of x plus 5. And so that would be like taking a negative 1 and distributing it, but then just adding stuff together. And then you have 7 minus x.
And now we need to add 7.
Well, if you add 7, then you've got 14.
Oh, okay, subtract 7.
You gotta subtract 7, but you gotta be careful when you're doing this, because now you've got this x and you can't forget it's negative, because it's being subtracted from something. You see, this is 0, 7 minus 7, so it's like 0 subtract x, which is a negative x. Then you got 4x plus 42. Not, see,
Subtract. Oh, you need to subtract 42. Now you-
yeah.
Now you have nothing to subtract.
Right. So we kind of got a little ahead of ourselves by working with the constants and not with the variables. It would have been easier to keep track of if we would have just started moving the x's around. But let's finish it. You just gotta follow your rules. You gotta get the x's together.
Actually, yeah, maybe I would put the, and then you have to do that.
Well, just look at this. How do I get the 4x gone from the right-hand side?
Divide.
Not divide, no. That'll never go away if you divide it.
When you divide the 4x, then you
So you got an x, you got an x, you got another x, and another x, and then you got 42 little boxes. And over on the other side, you have a negative x. So So let's just take those and subtract them from both sides. So if we add 4 negative x's, trying to draw a cheap algebra time. Add 4 negative x's, those will cancel each other. So over here we have to add 4 negative x's. Yeah, now you get negative 5x. So I'm going to subtract 4x, subtract 4x. That's a negative 5x. Equals 42. Now divide by how many? You have to divide by a negative so x comes out positive. Yeah. So now x is negative 42 over 5. I would like to show you something. I'll just do it real fast up here. Let's say we took this. Take that line and do it differently. Stick with the variables first. Watch. Plus x. Plus x. Now you have a 7 and a negative 5. Yes? 7 minus 5 is 2. Can you see where this thing's going now? You subtract the 44. And then you have a negative 42 is equal to 5x, which is where we were sort of here, except we just have the negative over on the other side. So when you do the division then by 5, you'll end up with a negative 42 over 5. You get the same thing, but it gets confusing when you have to move the x's around later on and you end up in a situation where they turn negative. You want to try to stay away from that. So that's that.